So Mark, thank you very much for the nice introduction. And I would also like to thank the organizers, Aaron, Astrid, and Mark for the very nice invitation and the opportunity to talk about this work that we recently put out on the archive, now basically 3 months ago. And was a project that started with my master thesis together with Jan Pawlowski in Heidelberg and Manuel Reichert now in Success, and now it has evolved into this very nice paper that we put out. So let me briefly set the stage and talk, even though the audience is already familiar with it. Talk a little bit about the asymptotic safety ideas, just for everyone to be on the same footing. So starting with the Einstein-Hilbert action, so starting with general relativity and trying to do perturbative quantization in the Feynman or QED fashions, turned out to lead to the existence of non-renormalizable divergences. This in the sense that when computing your loop expansion, at one loop you generate divergences that are proportional to the Einstein-Hilbert terms, so square root g is the cosmological constant, and then basically the Newton constant, square root gr. But then at every loop order, you generate further divergences that are not present in the Einstein-Hilbert action that you start from. So for example, at one loop, you have curvature square terms, and you can argue that these vanish on shell. And as soon as you go 2 loops, or you had matter at one loop already, you have non-vanishing divergences. For example, I'm listing here the famous or infamous, depends on how you look at it, Gorov-Sagnotti term. And exactly, and these are not vanishing, and this basically entails loss of predictivity in the sense that in order to renormalize the theory, you would need to measure an increasing and in the end infinite number of parameters in order exactly to fix your couplings. And so this has been known since last century, and then there was this idea around from Weinberg by the late 70s, and then put it to work by by Martin Reuter in the 90s, such that you maybe wish to give up the perturbative nature of your renormalization group flow and start to look for a non-perturbative UV completion. This is achieved via an enhancement of your an extra symmetry that you find in your theory, namely quantum scale symmetry. And this is, from the practical point of view, is realized by vanishing beta functions for some values, for some finite and non-zero values of the dimensionless coupling. So this is, in a sense, very similar or a generalization of what happens in QCD, where the ultraviolet limit of QCD is known to be asymptotically free. So the couplings, the beta function vanishes for vanishing couplings, and now in asymptotically safe quantum gravity, the beta function vanishes for non-vanishing values of the couplings. And then, as I mentioned, this has been worked out firstly by Martin Reuter, and it's now been 30 years of work in the direction of the gravitational fixed point. And so basically, via this quantum scale symmetry, the theory is ultraviolet complete in the sense that you can push your energy scale to higher and higher energies, and the divergences are tamed by this fixed point. And since it's been 30 years, basically, there's now a lot of work in many different directions. For example, going to more sophisticated truncations in a different degree of approximations. And there has also been a lot of work in understanding the interplay between gravity and and matter, how gravity can influence and solve for example, the standard model Landau poles, and the other way around, whether the presence of matter stabilizes or destabilizes the gravitational fixed point. And then recently, there's also been an increasing amount of studies on the interplay between the signatures. So most of the results till most of the results listed are basically in Euclidean signature, but recently exactly some Lorentzian computations have strengthened and have showed that the gravitational fixed point persists even in Lorentzian signature. And taking all of this amount of work, it's fair to say there has been an overwhelming amount of evidence in favor of the gravitational fixed point with and without matter. So what is hot at the moment? So what is still left to do in a sense? Well, first of all, there's the question, or the question that we also want to address is unitarity. So as I said, via this renormalization group fixed point and this quantum scale symmetry, you can achieve UV complete theory, but it's a different question asking whether this is a unitary theory in the sense that can one still think about this quantum theory as a probabilistic theory with all the interpretation of probability conservations, the probability should sum to 1, and so on. Then another open issue is definitely the definition and the computation of observables. So how can one connect this strongly correlated deep in the UV fixed point towards the infrared where we can measure the energies. And I mentioned these Lorentzian studies that have appeared in the last 5-10 years, and can one make this more concrete, even more explicitly? And then there's even more directions. So can the standard model emerge beyond standard model questions and so on? Cosmology, early universe, black hole physics, and much more. So for the purpose of this work, we are basically focusing on the first 3 points via achieving physical momentum computation. And I will explain in a bit what do we mean. And we're also in the line of work of these recent papers that I'm listing here, aiming at computing the full momentum dependence of, for example, graviton propagators, matter propagators, gravity-matter correlation functions, and so on. In particular, we had, I think, last month, a nice talk by Benjamin about these gravity-matter correlation functions. And so this is what's hot right now, and I'll now make our aim, the aim of this work, a little bit more concrete and draw this little cartoon. And for the sake of the argument, at the moment, I just want to do a little bit of momentum power counting, just to highlight, just to give a first handle on what the problem is. So for the finiteness, I consider 2 scalar fields that are denoting here by phi, scattering via the mediation of a graviton H into 2 other scalar field phi and phi. And I'm considering just the S channel process. So if I were to do, as I said, momentum power counting, how does the scattering amplitude for such a process behave? Well, there's a graviton propagator mediating the process, which is nothing but 1 over S, where S is the Mandelstam variable connected to the center of mass energy squared. And then for dimensional reasons, each vertex has to come as square root G times S and square root G times S. So if I carry out this simple product, I have basically a power counting that leads to G times S. And this already shows that I'm putting my probabilistic interpretation at stake. This means, so if we wanted to interpret unitarity in the standard sense, it means that the scattering amplitude is at the end connected to a probabilistic interpretation, to a probabilistic distribution. And as you can see by this momentum argument, as I increase my energy, basically as I increase S, Around the, let's say, around the Planck scale, this product will exceed 1, and I will lose this probabilistic interpretation. And this has been only classical momentum counting, loop corrections only worsen this problem. And I hope this little cartoon as shows kind of like the problem, but it can also highlight a possible solution. It can also highlight a way out, in the sense that if I can find that my interaction vertices, so here I'm labeling them as GN, but they'll be a little bit more general than just a Newton coupling. But if I can just find my interaction vertices to run as, for example, 1 over k squared, where k is some energy scale, then I have, in particular in the UV, then there's a concrete chance to have a finite m-bounded amplitude in this product. And it's not coincidence that I'm indicating this arbitrary energy scale as k squared, because this can be computed. It has been computed as so the running with the renormalisation group scale k, the IR cutoff of the Vertex equation, for example. However, this computation with the IR cutoff and then the identification with with an actual energy scale, it's a procedure that goes under the name of RG improvement. And it's a very good first approximation to get a handle, get a first insight on the behavior of computation, but as it explained nicely in these two papers, it eventually fails once, for example, considers multi-scale problems. So as the case of this amplitude. So I've depicted only the S channel, but there are obviously two independent energy scales, the S and T Mandelstam variables, and it is RG improvement will fail as soon as you have multiple scales. So that is basically why one has to go a little bit beyond this first approximation of RG improvement and try to achieve actual momentum computations in the sense of getting rid of the normalization group scale. And then you go on the market and you look for the two main approaches that permits these momentum computations. So on one hand, there's the form factor approach, as is nicely explained in these two papers, in these two reviews. And on the other hand, there's the fluctuation approach, as again explained in these two reviews. And for this work, we're focusing on a fluctuation approach. So in the language of the fluctuation approach, how can we upgrade the cartoon? Well, now I'm inserting these full black dots at the interaction vertices and at the graviton propagator, because I'm trying to encode the full non-perturbative dynamics of these interactions and these propagators. So how does the amplitude look like now that I've upgraded this to 1pi correlation functions? Well, there's the graviton propagator that I'm denoting as GHH, and then each interaction vertex, I will call this gamma phi phi h and gamma phi phi h. And at this stage, I want to point out that I'll focus on the RG invariant vertices in the sense that I can exploit a momentum-dependent redefinition of the fields such that the wave functions are reabsorbed now into the vertex. This has the immediate benefit that the graviton propagator will scale classically as 1 over p squared, where now p squared is connected to S, so the momentum transfer. But it's so the graviton propagator correction, the graviton quantum corrections are basically shifted in the vertex and will be important, and I'll show how they enter the computation. So if I carried out now this product, also considering the tensor structures going into the vertex, I have this combination of Mandelstam invariants, basically as dictated by Lorentz invariance. There's obviously the graviton pole. And then I'm encoding all the non-perturbative correction in this vertex function, v of S. And this is obviously a function only of Mandelstam S, because I'm focusing on the S-channel process. So the vertex function can only know about the S-channel variable. If I were to look at this from the T-channel perspective, then this will be a function of T and so on. And in particular, also this form of the amplitude here contains a first approximation, in the sense that I'm considering both the graviton transverse traceless mode and the graviton zero mode to basically contribute equally to this V of S. So I'm identifying the contribution from the zero mode and the contribution from the transverse traceless mode, such that I can write an overall vertex function. And at the very end, the vertex function contains as I said, the non-perturbative dynamics and the information of the fixed point, if any, and so on. And this can be accessed by basically resolving the form of this vertex, of this three-point vertex scalar-graviton. And since again I've reabsorbed the graviton propagator contribution into the vertex. So now, basically, if I can resolve if I can solve the non-perturbative equation for this vertex, I basically have the non-perturbative information on the amplitude. So I'll now go a little bit to the machinery and all the techniques that we're using to access exactly the asymptotically safe and non-perturbative dynamics of the vertex. So here's what the vertex will look like explicitly. So I have two scalars carrying momentum P1 and P2. I have a graviton carrying a momentum that I basically call PH. And now the vertex is just a function of two of the four momenta by momentum conservation. And on top of that, I also have the RG scale K. And in order to set up the flow equation for this type of vertex, we'll consider a tensor structure. And this tensor structure is basically made of minimally coupled scalars to gravity, massless, so I just have the kinetic term. And on the gravitational sector, there's Einstein-Hilbert with the gauge fixing and ghost action. And already the kinetic action is enough to generate a series of vertices. So in particular, I will have interaction of the type phi squares times h to the n, where h is the graviton and n goes all the way to infinity. And now I can take the Vetric equation formulated at the level of the quantum effective action gamma k, and by taking derivatives with respect to the fields, I turn this into an equation for the interaction vertex. And by the one-loop nature of the Vetric equation, I will end up with a one-loop look-like equation for the interaction vertex. And at this stage, I also want to declare my momentum variables, or the momentum variables that we are actually using. So as I said, P1 and P2 are the scalars for momenta, and I'll particularly be considering their magnitude, P1 and P2 in absolute value. Well, magnitude of P1 and magnitude of P2. And then there's this angular variable Z, that it's a four-dimensional angle in the sense, and all of these for the moment will be Euclidean, and later on I'll be discussing the analytic continuation to Lorentzian signature. So in order to set up the flow equation, once again, let me talk a little bit about the ansatz for the vertex. So this is the full vertex. We'll encode then the wave functions for each of the scalars and the wave functions for the graviton. And then I consider this tensor structure here just as stemming from the classical minimally coupled scalar tensor structure, and then I'm encoding basically the quantum correction for really the interaction phi h into this Newton coupling, running Newton coupling, or if you prefer, vertex dressing that encodes exactly the momentum running of the vertex. And as I said before, this will be a function of P1, the scalar momentum, P2, the scalar momentum, and on top of this, the renormalization group scale. So already at this point, there's a first exact results from 2015, where in the present setup, so since I'm using Landau, the Donder gauge, the scalar anomalous dimension is vanishing. And this happens even at the level of the momentum dependence. So I can consistently set the scalar wave functions to 1. And exactly with this, I generate a series of one loop like Feynman diagrams of this type. And I should point out that there's at most 2 scalar legs for each vertex, because that's the answers for the tensor structures. And inside all of these diagrams, there are like different couplings. So there's the defined point coupling between gravitons and scalars. There's also the 3-point graviton coupling, the 4-point mixed scalar-graviton, and so on, as well as anomalous dimensions for the gravitons and the regulator and so on. So with these vertex ansatz and with these exact results, I write down the flow equation for the dimensionless Newton coupling stemming from this vertex. So on the left-hand side, there's the beta function, so the scale derivative of the coupling, if you wish. And then on the right-hand side, there's the quantum contribution. So as I said, the graviton quantum corrections are encoded inside the graviton anomalous dimension, momentum dependent, and this I'm explicitly writing pH, but at the end this can be related to P1 and P2. And there is, of course, the Newton coupling rescaling all of this, and then there's the true contribution of the flow equation encoded in this strange guide that basically contains all the diagrams depicted here, and this is in virtue of the square root g. It's everything rescaled by g to the 1/2. So at this stage, I just chose the tensor structure to be the classical one, and if you wish, this is the exact renormalization group equation. And this term contains all of the different couplings, all of the anomalous dimensions, and so on. So in order to be actually able to solve this, we employ a series of approximations that I highlight now. The main one is justified by effective universality. So there has been these results in 2018 that since each of these diagrams technically comes with a different coupling, so the matter-gravity coupling, pure gravitational coupling, and so on. And there's no reason why in the strongly correlated regime this should be the same. But it was found that by taking into account the momentum dependence, or basically the momentum dependence of the fixed point of these couplings is very similar, is roughly the same. So this justifies the first and I think most important approximation going into this work, that basically both the 3-graviton coupling and the higher matter-graviton coupling are identified with the lowest one, so with G55H. And as exactly basically taking advantage of this effective universality. And then there's a series of other approximations. So, for example, we're not feedbacking the momentum dependence of the coupling into the loops, and there are vanishing cosmological constant, and also the graviton anomalous dimension is loop independent, or the loop graviton anomalous dimension is 0. And as I said, the tensor structure is just a classical one stemming from the scalar-graviton vertex. And in particular, there's one further input as taken from this paper of 2021 about the momentum-dependent graviton anomalous dimension. So this was already computed, 5 years ago, and we are basically taking that result and plugging it in this flow equation. So after all of this massage, how does the flow equation look like? So basically, all of the approximation have the advantage that now I can simply write a diagram function that encodes all of the contributions of these diagrams, and I can put all the dependence on the coupling into this G squared of P. And now the strategy is to resolve the momentum dependence in P and Z, as well as K, the RG scale of the sum of these diagrams, and further on integrate this equation to K equals 0. So how does the flow, or how does this diagram function look like? Since now I have three variables, so the two the two scalars magnitudes momenta and this angular variable z, I cannot plot in 4-dimension yet, so I'll show slices at 3-dimensional slices at fixed values of the variables. So for example, here on the left-hand side, I'm fixing the angular variable to be -1/2, and then I'm looking on the plane as P1 and P2, here rescaled by K. And of course, now the flow diagrams looks symmetric with respect to P1 and P2. Now I can look at a different slice. So I now fix P1 and P2 to have the same magnitude that I'm calling P squared. And then I look at the plane P squared and Z. And this is what the flow looks like. And this is highlighted because this is also the relevant or most relevant momentum configuration for the amplitude, and it will be the one that we'll be concerned about. And also, I want to point out that the dashed red line is the exact same momentum configuration of both slices, and this is what's known in the literature as momentum symmetric point. So basically, as I said, now that so we solve the diagram function or the flow in momentum dependently, and then we integrate the equation at k equals 0. That's where physics live, and where now we have like a momentum dependent vertex without any RG scale left, because this has been integrated to 0. And okay, this much for the whole machinery. And let me jump straight into the results and show the main point of the work. So a finite bounded amplitude in Lorentzian signature. So here I'm plotting the numerical data solutions. There's also a reconstruction going on that I'll talk a little bit about later. And so in red, the actual computational data. And this data, unfortunately, does not stand for experimental data, but this is like the numerical data of the computation. And then in blue, there's a line connecting all the data just to guide the eye. And as I mentioned already, this is the S-channel amplitude contribution, also taken in absolute value. It's Lorentzian in the sense there's like numerical analytic continuation from the Euclidean results. And since it's also in Lorentzian, I can go all the mass shell for the scalar m squared equal to 0, but equivalently could also be a finite mass shell for the scalars. I'm anyway interested in the very high energy limit, so as long as this is it's numerically 0, the boundedness of the amplitude is not influenced. And so some features of the amplitude, there's the linear scaling that I was talking about in the cartoon, where it's scaled basically as S. Then there's some fixed point. So the fixed point of asymptotically safe gravity is then reflected at the level of the amplitude. And I want to highlight that this is a momentum-dependent statement. So there's no RG scale, there's no RG improvement procedure going on. This is, if you had a powerful enough detector, this would be very close to what would you see. And then I also want to speculate that there's some funny structure going on interconnecting these two regimes in the transition. And at this point, it's merely a speculation, because as you can see, there are also error bars. And I just want to mention that this could be a gravable or Geon, depends on your naming, resonance that has also been found before. And yeah, but I would not trust it so much, because as you also can see, the error bars from the numerical reconstruction, so this is not the systematics on the functional on the FRG results is just on the numerical reconstruction, also tend to get the larger at the position of this peak. But I just wanna mention this resonance because I find it cool. Okay, now let me backtrack and how do we land on the Lorentzian result? And so I'll talk a little bit about the Euclidean side of the results. And here I'm displaying the Newton coupling or the momentum-dependent vertex dressing for this 5I interaction. And again, the red dashed line is what I highlighted before to be the momentum symmetric point. So some feature of this vertex dressing of this running Newton coupling, it is constant as at very low momentum where I have no quantum gravity contribution, and basically the whole theory follows GR as I already mentioned in the amplitude. But then, as soon as I hit basically the Planck scale or around the Planck scale, there's a momentum running of the vertex dressing, and this is a hallmark. In particular, it decays as p to the minus 2, where now p is the Euclidean momentum, and this is a hallmark of asymptotically safe quantum gravity at the level of physical momentum. And let me also point out that this happens regardless of the angular configuration Z, whose only role is influencing the transition. So you can see this as basically Z or angular dependent fixed point function that I'm also displaying here on the right-hand side. So on the x-axis, there is this 4-dimensional angular variable, and I'm plotting in blue the momentum-dependent fixed point function. So at p infinity, the RG scale has been integrated to 0, and I'm looking at the dimensionless version of the coupling. This is the dependence of the angular variable, and I'm contrasting this with the momentum-independent result. So now I send k to infinity while keeping a 0 momentum, and the two curves looks as a function of z rather similar. So they both present a peak, are roughly the same value of z, and they slowly decay. And I also want to point out that at z minus 1, this would be a collinear 4-dimensional configuration. The momentum-dependent fixed point is numerically small, but it's not 0. So I think it cannot be seen on the intensity of this axis. But yeah, the main point being that there exists a momentum-dependent fixed point regardless of the angular configuration. And this, as I said at the beginning of the results, is fed into the amplitude. So at this point, so this much for the Euclidean results, and it's at this point that I think it's worth to do a little bit of interlude on the momentum variables, because ultimately we want to analytically continue this to Lorentzian signature. So as I mentioned, the variable p and z are in Euclidean signature, both of them, and it has proven very difficult to perform a Wick rotation or a numerical analytical continuation in two variables. So the method we devised is to split up these Euclidean variables into the frequencies, p0, and then the three-dimensional, the three momenta, p and l, where now p is the incoming one and l is the outgoing one, as well as some angles. The role of the angles at the end is just to parameterize. These are three-dimensional angles, and just parameterize the reference frame. And p and l are three momenta, so they don't need any analytical continuation. And this can be reduced to just the Wick rotation of the frequency p0. So at the end, how does the Euclidean amplitude look like? Where there's a tensor contraction, so this combination of Mandelstam S that we know analytically and doesn't need any numerical Wick rotation, and then there's a combination of this vertex dressing as a function, as I said, of the vectors phi in, phi out, as well as the frequency. So now the trade-off is that I need to analytically continuate just p0, whereas all the other variables are basically parameters. And parameters, so it's a single variable but multiple reconstruction, because for every value of the parameter, the P0 analytical continuation has to be done, and only then the on-shell limit, because on the Euclidean branch that is not defined, only then the on-shell limit can be taken once I have analytically continued P0. So how does the Euclidean vertex look like? As I said, there's the tensor contraction, and then there's this vertex function encoding all the quantum correction as a function of P0. And basically the strategy is we fix the magnitude of the external vector P and vector L to be whatever, 0.1, 1, 10, and so on. And I look at basically the rescaled vertex. So this is the behavior of the Euclidean amplitude on the frequency plane. It's exactly a P0 squared times V. And again, linear here. And then there's a constant term once the fixed point regime is reached. However, we note that as cranking up the value of the external three momenta, so 0.1, 1, and then around 10, there's some funny structure appearing that will definitely complicate the Wick rotation and the analytic continuation. So now a little bit about this reconstruction procedure. So there's the Euclidean vertex dressing is computed numerically, and the strategy we devised to analytically continue this is to assume a Padé type function or a continued fraction of this type with coefficients that needs to be extracted from a fit on the numerical data, and then at fixed value of the external three momenta P, we derive the spectral functions. We compute the reconstructed vertex, namely we have a spectral function that is just a fit, and then we recompute back what would look like the Euclidean data. And at the very end, via the spectral function, we can also compute the on-shell Lorentzian vertex dressing. So now P0 and vector P are identified because on the Lorentzian branch, I can go on shell, vanishing mass shell, and compute the Lorentzian vertex dressing. And for all of this algorithm, I put a little bit of flowchart where, so basically, hopefully this will help to understand a little bit better. So fixed external value of the vector P, there are, let's say, M, for practical reasons, are around 100 Euclidean data. And these are numerical, so P0 and V. Out of these M Euclidean data, we sampled N of them, so a smaller value of them, in order to get the continued fraction, and from that, the spectral function. Once these two are computed, as I said, we compute the reconstructed vertex, basically. And then we carried out basically a chi-squared test between the reconstructed data and the actual result on the computation on the whole set of points, so on the whole M of numerical points. And at this point, if the chi-squared is failed, we start over with the sampling and so on. Whereas if the chi-squared is successful, the chi-squared test is successful, we can go on and compute the Lorentzian vertex dressing and then iterate this, sort of to take a statistical approach. And this has been taking inspiration from this paper where a similar procedure is done in QCD. But anyway, and then we need to repeat this whole procedure for every value of the external momenta, external three momenta, sorry, P between, let's say, 0 and 1000. So I hope I conveyed that this whole reconstruction has been numerically very challenging, but at the end, we managed to reconstruct the Lorentzian vertex to, in the end, get the amplitude that I'm showing you here again. And I hope it's also clearer the role of the error bars. They stem from this sort of statistical reconstruction procedure. And basically, they get the larger around this value of the peak because that's where the Euclidean vertex has more structure. As I mentioned, there was this little bump appearing on the Euclidean side as well. And so having more structure, also the error bars from this reconstruction gets bigger. But taken as it is, the Lorentzian amplitude is definitely bounded and finite, giving a good, giving a positive indication towards unitarity. And this is reflected since now I have an amplitude. I can also go on and compute the cross section. I'm just looking at again at the contribution from the S channel and the cross section. So the unitary indications for coming from the scattering amplitude are reflected at the level of the cross section, where now again GR recovered the funny peak-like structure appearing with huge error bars, and then a decreasing cross section. And so as a last point, I mentioned briefly about RG improvement, and now that we got access to the full results, or at least for the full results of this process, is there as a smart way of using RG improvement. Well, and also how to test how RG improvement fares. So I'm following this paper by Álvaro Pastor, Gutierrez, Jan Pawlowski, Manuel Reichert, and Giacomo Ruisi. Taking inspiration from those, we devised 3 different types of RG improvement. So there's the standard procedure, where no momentum-dependent computation is done, no analytic continuation. Simply the energy scale is identified with the RG scale, and this is depicted in green. Then one can improve this a little bit better and do an actual momentum-dependent computation, so integrate out the RG scale, and however avoid the whole reconstruction procedure that had all of these analytic continuation going in, and just identify the Lorentzian Mandelstam S with your Euclidean momentum, and this is depicted in dashed orange here. Or as a last point, one could cheat, knows the full result, and construct basically a vertex trajectory, knowing the fixed point of this amplitude of this vertex and feeding it as such. And by construction, the red adapted RG improvement will reproduce exactly both the infrared limit and the high energy limit of the amplitude. Also the orange, so the Euclidean RG improvement gets close enough, but all of them will miss this peak-like structure if you want to take it seriously, but all of them will miss that transition regime. So this last part brings me to my conclusions. So in this work, we've computed exactly the full, or as full as it gets, for the amplitude momentum dependence of the vertex dressing. We found, so through the physical asymptotic safety property of this vertex dressing, we found a finite and bounded amplitude, at least in the S channel that I'm depicting here. And overall, this can be taken as a good indication for unitarity. And I want to mention again this gravable that has been found recently, also from acidity perspective, and can be a numerical artifact as well as an approximation. It's also worth to have a more detailed look at it. And a little bit of outlook on this work. So it's definitely worth to discuss all the channels, because I give a big discussion of S channels. So what about for example, the T channel? Well, if you look at the T channel hard scattering, so high energy limit S to infinity, there is a divergence that the vertex cannot tame. So in this mediated amplitude, the vertex, as I said, will just be a function of the T variable, and at fixed T, this will diverge as S squared, no matter what your asymptotically safe correction to the vertex will be. And in fact, this is an indication of about the fact that the mediated amplitude is only part of the full scattering amplitude that, at least in the 1PI language, also contains the contact term interactions. And only once one has a bigger picture or a more complete picture of both the contributions, can make definitive statement about unitarity, contrast this to partial wave bounds, and so on, as is also nicely explained in this paper by Benny. And also in that directions, I wanted to highlight to stay tuned, because there's been some work in progress, exactly to include also these contact interactions coming from a pure Lorentzian computation, and in the end take this and draw more definite conclusion about unitarity. So that be all, and thank you very much for your attention.
All right, thank you very much, Angelo, for the nice talk. 1 second.